In the name of Allah, the most gracious, the most merciful. Praise be to Allah, and peace and blessings be upon the messenger of Allah, our master Muhammad, and upon his family and companions. After finishing the general discussion in the first episode and talking about it in the second episode, we begin with you a new episode, a new challenge and practical information that will benefit you in the job market about what is the basic theory of the current transformer, or what is the principle of operation of the current transformer. When the current from the primary winding, which is connected in series with the circuit, flows, it creates a magnetic field. This magnetic field, when it intersects with the cross-section of the core, generates magnetic flux. This magnetic flux moves due to the magnetic motive force through the core to intersect with the secondary winding. When magnetic flux intersects the secondary winding, it generates an electromotive force causing the secondary current. The maximum voltage at the current transformer is the knee point voltage. Each current transformer has a unique magnetization curve showing the relationship between voltage and excitation current. This current drawn within the core is a small part of the secondary current. On the magnetization curve, there's a knee point. It is a curve that shows the relationship between the voltage generated at the terminals of the secondary winding and the current that causes the flux, known as the excitation current. This is the current drawn within the core, and it represents a small part of the current generated on the secondary side, which is the current drawn inside the core, as shown in the diagram. On the magnetization curve, there is a point called the knee point. This point is where the curve transitions from one shape to another, or where it shifts from a normal phase to an abnormal phase. And this abnormal phase is referred to as the saturation phase. What? Saturation? The knee point is defined according to the IEC standard as the point at which a 10% increase in the voltage value causes the magnetization current to rise to 50%. In other words, it's the area where the current transformer enters the saturation phase, and the CT should operate in the linear region before this point. As for the definition of the knee point according to the IEE and ANSI standards, IE and female standard, it is the point where the characteristic curve intersects the 45-degree line with the magnetization curve. Comparing the two definitions on the graph, the knee point per IEC is higher than per IEE. But what does it mean if the CT enters saturation? It means the CT won't generate current in the secondary, nearly zero, or may produce distorted current affecting the relay's decision. This leads to improper relay performance unless resolved. This problem arises with a significant fault moment increase causing high current the core can't handle, leading to saturation. Here it means the increase over time stops and the rate of change of flux with respect to time becomes zero. Since current is proportional to this rate, if it becomes zero, the current theoretically becomes zero. A problem arises when there's a significant increase in fault moment value, causing a high current that the core can't handle, leading to saturation. This means the increase halts and the flux's rate of change becomes zero. Since current is proportional, if it becomes zero, so does the current. The iron core is like a road with many cars, having a certain capacity. If cars exceed this capacity, traffic halts. This means that the rate of change of the flux with respect to time has become zero. Since the current is directly proportional to the rate of change of the flux with respect to time, if the rate of change becomes zero, then the current will also theoretically become zero. The iron core in this case is like a road with a large number of cars. This road has a certain capacity and a limited number of vehicles. If the number of cars exceeds the capacity, traffic will inevitably come to a halt. At that point, we say that this road has saturated or that it has become saturated, and thus it has not achieved the purpose for which it exists. Let's assume a three-phase fault occurred causing high fault current saturating the CT wing. How to remove residual flux in the CT core? Residual flux causes DC offset. It distorts current like DC voltage applied to transformer. Increasing DC leads to quick saturation and overheating. DC offset value depends on breaker closure and RX value. Duration depends on RX. DC offset is identified by loud core sound. Core sound indicates DC offset or open CT secondary. Keep in mind that if you apply increasing DC to the transformer, it will quickly go into saturation and will experience overheating. So there's a difference between DC saturation and AC saturation. The value of the DC offset in the circuit depends on the moment the circuit breaker closes and on the value of Rx in the circuit, while its duration depends only on the value of Rx. We can easily identify the presence of DC offset in the primary current by hearing a loud sound coming from the core. If there's a sound coming from the core, it means that there is a DC offset or that the secondary circuit of the CT is open.
The DC aspects of triple cancer are very important because they can lead to a significant level of magnetic flux in the CT center. An important situation occurs if the CT center has a large magnetic field from the previous cancer, and then a second triple cancer occurs.
This is what happens. Guarding maintaining the maintenance of the maintenance of the maintenance of the maintenance.
Condition is added to a growing remnants flux from previous cycles.
Sometimes the CT scan will not convert to the wrong size correctly.
We revisit the question, how can we solve the issue of saturated CT or residual flux? This is addressed by applying high voltage to the CT's secondary windings, exceeding the knee point voltage, then gradually reducing it to zero. This cancels the residual flux by creating an opposing flux known as CT demagnetizing. Another solution is to leave the core for a period, allowing the CT to generate a ghost current in the secondary, eliminating remaining flux until normalcy returns. In one station, this ghost current, caused by residual flux despite no primary current, led to a breaker trip, unnecessarily taking part of the station offline. To solve the problem of residual flux in the core, leave it for a period. Based on the circuit value, the CT then generates a ghost current in the secondary, eliminating the remaining flux until normalcy returns. In one station, this ghost current, caused by residual flux, despite interrupted primary current, led to unnecessary breaker tripping and station downtime. To prevent this, a special CT type, TBZ, is used. It cannot retain residual flux, making its remnant negligible, thus preventing breaker failure. So, it was agreed to use a special type of CT that cannot retain residual flux inside it, meaning its remnant is almost zero or negligible. This type is called TBZ, and it's used for breaker failure to prevent the problem from happening again.
Inspiring the revival of a nation.